Okay, one thing which I forgot in our last class, uh, to mathematically prove the fact that in an in the kind of ohm meter that we have discussed, uh, which is here, the measurement error, relative error in measurement will be minimum at the near the middle part of the scale. Okay, so let us do that quickly. Okay, acha. So this is roughly the circuit.
Sir, please make it full screen.
Full screen. Uh, where is the option full screen? Now Rx, then
Sir, I'm talking about in Teams. I can see screen
no.
on your profile.
Okay, that is
You
in
can
your
select
hand.
and pin it. You can
Yeah.
select it and pin it.
Okay, sorry.
Okay, I mean, Teams control is in your hand actually.
Sir,
Yes. Yes.
I think in the first problem set, the answer of the last two questions have not been given. So, sir, can you please check that?
Okay, I mean, I will do. I mean, answer means basically I have to calculate and give what I am getting as the answer. And you have to verify whether I am also correct or not. I will do that. Thank you. Yeah.
Okay, sir.
Uh, okay, acha. Now, the reading of the meter or deflection of the meter theta is given by the current that will flow through the meter, which is E divided by Ri plus Rx. This multiplied by some constant maybe, and E is also constant, so let me just write a constant divided by Ri plus Rx. This is the meter reading. Now I can do this derivative d theta by drx, that will be minus k over ri plus rx. By the way, what is ri? Ri is the total internal resistance of the meter. Okay, that includes R1, R2, little r, everything, Rm, meter resistance, everything. Okay, acha. Now I can write drx by d theta, that will be rx plus ri by this constant. And what is this? This is the amount, I mean, if you make us a little error in measuring the deflection, what will be the change in your measurement or error in your measurement? Okay, so if you make say 1 degree mistake, then how much error you make in resistance measurement. Now relative error or percentage error, per unit error, that will be drx by d theta divided by rx. So this quantity tells or gives the per unit error if you make 1 unit mistake in your deflection measurement. So that will be rx plus ri by rx into k. Here I have a mistake.
Sir, it will be Ri plus Rx whole square, right?
Yes, thank you. Right, now it's fine, and there is a k. Okay, acha, now we would like this to be the minimum. So to minimize this quantity. Okay, so let us minimize this, and for that we will differentiate this quantity with respect to Rx and equate it to 0. So we are finding for what value of Rx we get minimum relative error. So we will find this and equate it to 0. Okay, so for that let me differentiate this quantity. So differentiate numerator 2 Ri plus Rx times, this is fine. Yeah. Differentiation of numerator, then differentiation of denominator is 1 minus numerator as it is, and differentiation of, here I have Rx and here I have 1 divided by Rx square and 1 over k minus, that is constant. Okay, so we want to minimize this quantity. Actually, not minimize this quantity, we want to minimize the mod value of this, which is this. Okay, otherwise negative error or positive error does not make any difference, but the absolute value of this relative error should be small. Okay, so fine, so this should be equal to 0 for minimum, and that implies here the numerator should be 0, so 2Ri plus Rx multiplied with Rx, that should be equal to Ri plus Rx whole square. Now let me cancel this square with this term, and this implies Rx should be equal to Ri. So this is the value of the unknown resistance for which we will get minimum relative error. Yeah, this could also be the maximum. Whether it is maximum or minimum, to decide that we have to differentiate this quantity once again and make sure the second derivative is positive. That I am leaving as a homework, you check it yourself. Okay, that will come out to be positive. So this is the condition for minimum relative error, condition for minimum relative error. Okay, so that means at the center of the scale, near the center of the scale, we will get minimum relative error. Okay, acha. Now we will start a new topic. So previously we have seen that we can measure a resistance using a voltmeter and ammeter, and so here are the two possible schemes. Okay, and we know neither of them will work always. This scheme is good if Rx is smaller than voltmeter resistance. This scheme is good if Rx is higher than Ra. Now we are going to talk about small resistance, low value resistance measurement. So therefore this scheme is not good, we will use this scheme. So let me copy this. Okay, acha, fine. So this is this scheme to be used. Next, we are talking about actually very low resistance measurement, and there we will see some other problem will arise. Okay, so very low means, I mean, the resistance could be, for example, smaller than order of 1 ohm or less. Okay, acha. Now the problem is as follows. This is just a circuit diagram, but when we do actual experiment, we have to connect this resistance, voltmeter, ammeter, everything with wires, with leads, etc. Now suppose I have a small resistance box. Inside that we have the resistance, and it has 2 leads, 2 screws, 2 terminals, where we will connect the voltmeter, ammeter, etc. Let me draw them bigger. So this is the actual resistance inside Rx. These are the connecting leads or junctions, and here suppose I connect the voltmeter and then the ammeter, like this. Now this junction, this screw also has some resistance. Okay, so you can think that this junction will contribute to some resistance in all these 3 branches. Okay, so effectively you can think that this is a point connection, I mean just a point, but it contributes some resistance in all the adjacent branches. Okay, and these resistances are also small. Okay, however, the values of these resistances, that is not very well known, well predictable. That will depend on how you connect this screw, how much tight you make it, all these things. So these resistances are not, I mean, not predictable, unpredictable. That is the main problem. In measurement, if anything extra comes, and if that is well predictable, well known, that is not that a problem, if you can predict that well. But if something is not predictable, not well known, that is a bigger problem. Okay. Now what will happen? Now when you measure the voltage and the current and divide voltage by current, you are actually measuring not Rx, rather Rx plus this resistance. Okay, so let me call this as little r1, little r2. What you are actually measuring is Rx plus r1 plus r2. So voltmeter reading by ammeter reading, that will be Rx plus R1 plus R2, which is not equal to Rx. Normally R1, R2, little R1, little R2 are little, are small and not a problem, but when this Rx itself is small, then you are making a large percentage error, large relative error, and that is the problem. Okay, so because we are talking about low resistance measurement, this little R1, R2 are not little problems but big problems. Now how do we get rid of this? The solution is very clever, a very clever one. It is called 4-terminal resistance. A resistance is expected to have two ends, two terminals. So 4-terminal, this name is very surprising maybe, but the meaning will be clear very soon. So here in this diagram, let me repeat this diagram. Here we will take a resistance box which has 4 junctions, 4 screws or terminals like this. This Rx is inside, and from here we will get 2 terminals out, and from here we will get 2 terminals out. Inside here we have a join or a connection, but that is a fixed joint, that is inside the box, that is permanently soldered. So here nothing is going to change. Okay, but these screws are meant to be connected with external circuits, and we will connect things like this. Say we connect 2 ends of our voltmeter here and the 2 ends of our ammeter battery circuit here. Now these 2 are screws, so they will contribute to unpredictable varying resistances. So they will contribute some resistance here, some small resistance here, 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 here. And these resistances are again not constant. Every time you do the experiment, every time you connect it, they are going to be, they will vary. So these are unpredictable resistances. But now you observe, if I measure this thing, voltmeter reading by ammeter reading, my claim is this will be very well approximated to Rx. Why? Okay, to see that, let us assume current I is flowing. Okay, actually let us take I equal to 1 ampere. So meter reading is 1 ampere. That means whatever is the voltmeter reading, that will be equal to resistance according to our formula. Achha. Now this 1 ampere current is flowing like this, and that will cause some voltage drop here. But this voltage drop is in series with the battery circuit, so battery may also have some resistance, etc. So this voltage drop is something similar to voltage drop here, which will not bother us much. But this 1 ampere current will flow, continue to flow here, I equal to 1. And here, from this point onwards, it will have 2 paths, one through Rx, one through this voltmeter. However, normally voltmeter resistance is much higher, and there is something also called potentiometer, which we will study later, for which we can take this resistance to be infinite. So that means this current will flow through Rx only, or at least most of it will flow through Rx. Okay, and it will come out and then it will go like this. Okay, and now voltmeter reading Okay, voltmeter reading is how much? Voltmeter reading. So voltmeter measures potential difference between these 2 points. Okay. However, that is also very close to the voltage difference between this point and this point, because this voltage difference from here to here has 3 components, one here, one drop here, one drop here, and one drop here. But these are small drops compared to this drop, because voltmeter resistance is high compared to the junction resistance, which are negligible, I mean much smaller than this. So therefore voltmeter reading, which is the voltage between this point and this point, is also same as the voltage between, very much same as this point and this point. Okay, so that is I very close to, I mean, this by this I mean this is very close to I times Rx. Okay, so therefore when you divide voltmeter reading with ammeter reading, you will get Rx. Okay, so
Sir, why can we not make similar arguments in the previous circuit?
yes, that's a good question. Now let us come here. Okay, acha. In the previous circuit, voltmeter reading is basically potential between these 2 parts actually, but I can say, oh, that is very much same as the voltage between this point and this point, because this drop, I mean this drop and this drop is much smaller than drop in the voltmeter. That is true. However, acha, now how much is this drop from here to here? How much is this drop? That will be same as current in this branch multiplied by these resistances. Again, if this current is I, most of it will flow through here, I, and very little amount will flow through the voltmeter. That is also true. But now the problem is this voltage is I. So this voltage is I multiplied with Rx plus R1 plus R2. Rx plus, let me write it the other side. Let me write it here. This is I multiplied with Rx plus R1 plus R2. Okay, so that is the problem. Here we have R.
Sir, means the main difference is that in the 4-terminal resistance there was no internal resistance at the junctions of the terminal. That's why we could measure directly the total voltage drop across Rx, right? Means there is no resistance in the junction inside the box.
This junction you mean?
Yes, sir. Yes, sir. If there had been resistance, then we couldn't have measured the correct voltage, right? Means if there had been some.
Here also there are resistances. So this may also contribute, actually has small resistances like this. Any junction, why will it not have any resistance?
And sir, how are we measuring the exact? Means there will be some.
But that is not a problem, because these red resistances are fixed. Okay, therefore this red resistance which I am pointing now, that you can think, okay, we are actually measuring this red plus this Rx plus this, and these 3 things together I am calling Rx. That is fixed, that is not going to change, because this soldering is not going to be altered. That is the point.
Yes, sir, okay.
Okay, but here this connection is going to be altered. Okay, so that's what I was saying. Any extra thing in measurement is not a problem as long as that is predictable and fixed. But here that is unpredictable. Okay, I guess you need to think over it, because this is a very subtle argument, and unless you think again and again yourself this may not be clear to you. Okay? Acha. Let me give you another example, another very nice example where 4 terminal resistances will be very useful. Okay? So consider shunt in an ammeter. Okay? So suppose I have an ammeter with say resistance Rm equal to 99 ohm and full scale deflection current equal to 1 milliampere, and with this ammeter I want to measure 1 ampere current. Okay, let me make it 10 for ease of calculation, and I want to measure 1000 milliampere with this. How will we do that? We have to put a shunt in parallel, and value of this shunt, if we want to measure 1 ampere current, to measure 1 ampere, the value of Rs should be how much? You can calculate it. It will come out to be 1 ohm. Let's check quickly. So 1 ampere flows here, 10 milliampere flows here. So here we want 1000 minus 10 is 990 milliampere. Okay, so this voltage theoretically 10 milli into 99. Here also 990 into 1, they are same, correct. So we need to connect a 1 ohm resistance in parallel. 1 ohm is a small value, okay, at least much smaller than 99. And now if we use say a 2 terminal resistance like this ammeter, and a 2 terminal resistance I will take, and here I connect the 2 ends of my ammeter, and from here suppose I take the external connection. Now these junctions can again contribute small resistances here, here, everywhere. Suppose this is now 99 ohm, this is 1 ohm. Now just for an example, this is to illustrate the idea, let me assume that these small resistances are all 0.5 ohm. Okay, all of them I am taking 0.5 ohm for simplicity. Okay, now let us check, does this contribute to any error in current measurement? Let us check. Suppose when full scale deflection current flows here, I equal to FSD equal to 10 milliampere, then according to our previous calculation we will think that here let me call it IM and this is we will think I equal to 1000 milliampere or 1 ampere. We will think, because that's what we calculated here. If 10 milliampere flows in this branch, then in the parallel branch 990 milliampere should flow, so here 1000 milliampere should flow. That's what we are thinking. But is that true? Is it true? Let us check. So 10 milliampere is flowing here. That means voltage drop from here to here, okay, that is 10 milliampere multiplied with this resistance plus this 99 plus 0.5 plus 0.5 ohm, that is equal to 100, so 1000, correct? 1000, yeah, 1000 ohm, sorry, 1000 volt. Okay, so now this current, call it IS, shunt current, IS will then be, oh yeah, 1000 millivolt, yeah, 1000 millivolt. It will be 1000 millivolt divided by these three resistances, 1 plus half, 1 plus half, that is 2 ohm. So here I have 1000 by 2, 500 ohm, right? So 500 milliampere. Okay, so then this current I, which is at IS plus IM, that is 1 ampere plus 0.5, correct? 1.5 ampere. Is my calculation all correct? Please check once.
10 milliampere plus 500 milliampere.
Anything wrong?
So IM is 10
10
That's why
milliampere
510
plus
milliampere.
510 milliampere it should be.
510, oh sorry, 510 milliampere. Okay, so this is the actual current. Okay, Acha. Then but we are thinking this is 1000 milliampere. Okay, according to our calculation, calibration, this is 1000 milliampere, but actually this is actual value, and this is estimated, guessed, thought value, something like that, estimated. And the error, so error or relative error is huge. So out of 500, almost 50% error. Almost like, in fact, 100% error, depending on what you are dividing with. Okay, so double measurement we are getting. So this is a huge error. Okay, now let us do the same thing with a 4-terminal resistance. So now let me take a 4-terminal resistance. One, two, three, 4. Here I have my ammeter, and the way I will connect is this. I will connect the ammeter here, and these two will be connected to the external circuit, and we are measuring this current. Okay, fine. Here also I. Achha. Now this is 99 ohm. The resistance between these 2 points is previously known, calibrated to be RS equal to 1. But these junctions will add extra resistances. Here, 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 everywhere. Here, here. Okay. And let us again take all these resistances to be half ohm. Okay, all of them half ohm, 0.5, 0.5, everywhere. Okay, all 0.5. I am not writing everywhere. Achha. Next, now if I get full scale deflection current here, if this is equal to FSD equal to 10 milliampere, okay, then I will think that I is equal to 1 ampere. We will think. But again the question is it true? Let us check. So here we have 10 milliampere current flowing, and so that means the voltage from here to here, that will be 10 10 milliampere multiplied with 99 plus half 0.5 into 2 ohm, that is 1010 millivolt. Okay, then is this current is will be 1010 millivolt divided by this resistance, which is 1. Okay, and that is fine. That is 1 point.
Sir, should it not be 99 plus 0.5 into 4?
So it would be into 4.
Yes, 0.5 into 4. Yeah, actually I did that. That's why it's 101. I wrote it wrongly, but mentally I calculated it to be times 0.5 times 4. Yeah. Okay. 1010 by 1. So this will be milli. So that will become 1.01 ampere. Very nice. So we are thinking it to be 1 ampere, and it is something's wrong. This is is correct. 1010 by 1 is okay. Oh, now I is equal to is plus im. That will be 1.01 this value plus here 10 milliampere. 10 milliampere means 0.01 ampere, so that is 1.02 ampere if I have not made any mistake. But one thing is for sure, that this is quite close to 1 ampere. Okay, so relative error is approximately like 2% only. Previously we are getting 100% error, but this is, previous one is not usable, this one is much acceptable. So that is the beauty of a 4-terminal resistance. Is everything fine so far?
Sir, in this case, the current is more like, wouldn't it damage the ammeter?
In this case?
Yes.
No, the ammeter, we have set up this thing to measure up to 1 ampere current. Okay, and we estimated, in theoretically previously here, when 1 ampere current flows, then we get 10 milliampere deflection. Okay, now full scale deflection. Okay, now here what we see, that when this is 1.02, okay, then we will get full scale deflection. So we are supposed to allow 1 ampere current here. That's how our and 1.02 is very close to 1. Okay, anything else? Okay, then we will talk about another new topic, but related to low resistance measurement only. Okay, and this the title of this topic is called Kelvin double bridge. We will come to this, but before that, we will come to this topic. But before that, let me give you the background of this topic. So recall Wheatstone bridge that you have studied in school. Okay, here we have some meter, and this is how we draw it. Call it P, Q, R, S, and at balance, you all know at balance means when we get null or zero deflection in the meter, you can prove that P by Q equal to R by S, and this can be used to measure an unknown resistance. Okay, for example, if R is unknown, this is unknown, then you can pick other resistances to be known and variable. This is unknown and not variable. You change these other resistances until you get balance. When you get balance, then you can say, okay, R then will be from here P by Q into S. You know all these resistances, so you can get Rx unknown. Okay, now suppose the unknown resistance that we are measuring is low, is of a low value. Okay, is a small resistance that we are measuring. Okay, now one thing may also happen, that if Rx is small, and then to get balance, left side is a small value, so right side should also be a small value, and for that it may require that either P or S is also small. Okay, so we may need that. Okay, so we may need one small resistance also in the right side. Suppose we are taking P and Q to be of medium value, okay, then S should be small, so we may need S to be small. Okay, so now we are in a situation where this is small, this is also small. P and Q, we can take them to be of medium value, no problem. So we have seen, I mean, the problem occurs in low value resistance, I mean here, but for medium value resistance, these junction resistances are not problematic. So whenever possible, we will use medium value resistances, but so that these junction resistances are not a problem. So in our Wheatstone bridge, since we know low resistances are problems, so we will take, say, P and Q to be of medium value, I mean where junction resistance is not a problem, but we may need S to be small because left side is small. So for these two resistances, junction resistance will be a problem, and that is the introduction of my new topic. Okay, so let us see this in detail.
Sir,
Yes.
can't we take Q to be very large or P to be small?
Let me just tell you one thing, that very soon, today or tomorrow, we shall see that very large value resistances also have problems associated to them. Okay, so very large, very low value resistances are problems, medium values are fine. Okay, so don't take Q to be very large. That we will see to maybe tomorrow. Okay, fine. Yeah. So now, so suppose these resistances are two terminal resistances. So let me erase these connections and draw the leads explicitly. Okay, now what we will do, we will connect maybe this with this, this with this, this with this, and this you may connect wherever you like, maybe here. But notice that these junctions will add unpredictable resistances here, 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 everywhere. One thing you may do, maybe you erase it here and connect it here. Maybe you erase it here and connect it here. Then one thing is nice, this little resistance is not going to create much problem because this is coming in series with Q, and Q is not a small value resistance, it's not a low value resistance. So if you add something small with something significantly bigger, that is not going to give much relative error. So this resistance, okay, no, not a problem, not a big problem. Similarly, this resistance is not a big problem, not a big problem. And so is true for this. But here, these resistances, this one, this one, this one, this one, they are coming in series with a small value resistance. And when you add something small with something small, relative error is big. So these are big problems. Big problems. This one is also a big problem. This one is also a big problem. Then this one is also a big problem. Okay. I have made an ugly diagram, but hope the message is clear. So do you follow what is the problem? Problem is that the small resistances are coming in series with other small resistances, and now in this equation, suppose I call this little r1, little r2, little r3, little r4, okay, then actual balance equation will be this rx plus little r1, little r2, this should be equal to p by q multiplied with s plus little r3, little r4. Oh, in fact this will also come, this and this. But okay, I can call this together R3, this together R2, so then R3, R2. Okay, now suppose you have set S to be 1 ohm, and these are also say like 0.2, 0.3 ohms. So then here in your equation, you have almost like 50% error. Okay, also this side will contribute error. So small things getting added to other small things causes large percentage or relative error. Do you agree? Anyone who does not add, anyone who has a counter argument, any counter argument, counter logic? Okay, fine. So this is the problem. I think I cannot give you the solution of this problem today. We do not have that much time. But let me do some small maths which I will use tomorrow to give the solution of this today's problem. I am going to draw a bridge which has, let me first draw a Wheatstone bridge. 1, 2, 2 resistances, then 3, 4. I am going to draw the Wheatstone bridge in a slightly different way than you have seen in your books so far. This is a Wheatstone bridge, right? Let me call P, Q, R, S. Here we have a meter. Normal Wheatstone bridge. Okay. Now let me do some modification to this bridge. I will see this carefully. I will erase this part. Here I will add another resistance, call it gamma. Here I connect another resistance. Here I connect another resistance. Call it A, call it B. Okay. So this is the modification done to a normal Wheatstone bridge, and this is called Kelvin's double bridge. Today we shall just find the balance equation for this bridge. In this bridge, P, Q, A, B and one among R and S are known and variables. Maybe this. R may be the unknown. Okay, fine. Now, the way to use this bridge is you connect them in this way and then vary this P, Q, A, B, S until you get
Gamma is unknown or known?
gamma is also unknown, but we will not care about it. You will see. Gamma is unknown. Okay. Acha. The way to use it is to vary P, Q, A, B, S until you get the balance or null in the meter, and then we will find the balance equation. From that we will get Rx. But whenever you use this bridge, make always sure that P by Q is equal to A by B. So if you are changing P, also change A, or if you are changing Q, also change B, so that whenever you are changing any of this P, Q, A or B, this condition is always maintained. So maintain this. This you have to do. This is the requirement. Okay, fine. Now we will find the balance equation.
Sir, why is this requirement means? How is this coming? Why is this a requirement? P by Q equal to A by B?
That you will see very soon. But for now, take it as a prescription for me. I am telling you, make it sure. Okay. What is the benefit? We will see in few minutes. Achha. Now to find the balance equation, what I will do, I will convert this in a Wheatstone bridge. Sorry. Copy, paste. To convert this into a Wheatstone bridge, I will use a star delta conversion. Here. There was a delta, and now I am going to convert this into a star equivalent circuit basically. Okay, Achha. So let me write here, this resistance will have a value B gamma divided by A plus B plus gamma. This resistance will have a value, let me write here, A gamma divided by A plus B plus gamma. And this resistance will have some value which I do not need. Let me put the battery here so that I can get some space. So that I can do something here. Okay. Now the balance condition. So now you see this is a Wheatstone bridge. Okay. How is this a Wheatstone bridge? It has 4 arms. From here, this is one arm. Okay. This is the other arm. Then this and these two resistances together is the third arm, and this is the fourth arm. So this is a four arm Wheatstone bridge. Between these opposite two terminals I have battery, and between these two opposite corners I have the meter. Okay. So now I can write the balance equation for a Wheatstone bridge, and that is this P divided by Q, P by Q is equal to these two resistances together are X plus this resistance, which is A gamma by A plus B plus gamma, divided by S plus this resistance, S plus B gamma by A plus B plus gamma. Okay, this is just from Wheatstone bridge principle. But also, since we are maintaining P by Q is equal to A by B, I can write this. This is coming from Wheatstone bridge principle, and this is coming from what we have done. Okay. Now let us simplify this. Let us start from here and simplify this. So this is equal to, I will write A gamma by A plus B plus gamma divided by B gamma by A plus B plus gamma. I am just multiplying the numerator and denominator with the same factor gamma by A plus B plus gamma. Now let us apply component to whatever, what do you call component to dividend to something. So let me subtract this and this. So you will get Rx plus this minus this. Okay. So that will cancel. Let me write A gamma by A plus B plus gamma minus A gamma by A plus B plus gamma whole divided by S. This plus B gamma by A plus B plus gamma minus B gamma by A plus B plus gamma. This is equal to Rx by S. So we have got a simple balance equation P by Q equal to Rx plus S. This is the balance equation. Please notice that we have got this by virtue of the fact P by Q equal to A by B, which we have ensured ourselves. During our experiment, we will vary P, Q, A, B together, so that this is P by Q equal to A by B is maintained, and that's how we get this. If we do not maintain P by Q equal to A by B, then also we can get a balance, but then at that balance condition, P by Q need not equal to Rx by S. The nice thing about maintaining PQ equal to A by B is that our balance condition does not depend on this resistance gamma. If we do not make sure P by Q equal to A by B, we may still get a balance, and then if we derive the balance condition, then the balance equation may have gamma. But here the equation finally does not depend on gamma. Does not depend on gamma. This is the nice thing. Why is it nice? That will not be clear today. That I will tell you tomorrow, when I will use this fact to give the solution of this problem, where we have seen that these little resistances create problem in a Wheatstone bridge. These junction resistances create problem in a Wheatstone bridge. So today any question?
So what if we put gamma equal to 0?
I actually do not, I mean, what is your point? I mean, you are trying to,
Sir, instead of adding a delta bridge, why don't we add a single resistor in series with a detector?
so you are saying that why we not make a star bridge from the beginning?
Yes, sir.
Okay, so tomorrow we shall see that to solve this problem, we will modify this bridge where we will use 4 terminal resistances, and there naturally this delta formation will come. That will come naturally from the way we make the circuit. And then to simplify that, we will convert that into delta. That we will see tomorrow. So today the story is not complete. I mean, the interesting part is not done yet. But you just remember one thing, that we have derived a balance equation for this bridge that we will use tomorrow. Any other question? Any question from today's topic, previous topic? Achha, one thing, one question that many of you, several of you have asked previously, and where I did not, possibly still I do not have a very concrete answer, but one thing I thought later is this. So this is the good old capacitor battery problem. Okay, I will motivate this in this way. Suppose I give you a very simple circuit problem. I have 2 batteries connected in series or parallel, E1, E2, and I ask, there is no resistance anywhere. I ask how much current is flowing. This is a question that I am asking. How much is I? What will be the answer of a mathematician? The answer will be, solution does not exist.
Correct.
Yes?
Any current can flow.
No, in fact, if E1 is not equal to E2, then there is no value of current, there is no value which will satisfy KVL. So
Yes,
solution does not exist. Yes?
Theoretically means does not exist, but practically there will be some source resistance, so some current will.
Yes, practically there will be some small resistance, and we will say very large amount of current flows. Okay, and to model
So
that,
we can't even write the KVL equation. Like,
We can't even
across
write-
what will the current drop?
yeah, I mean, we can't even write KVL. I mean, or we can write, but then we will say, oh, this is not a problem which has a solution. Okay, so if I write KVL, tell me what is the solution to the equation E1 minus E2 minus 0 into I equal to 0. There is no solution. That is one way of getting away, you can say, from this problem. Achha. In the same way, now come here. The moment I close the switch, after that, this is E, this is C, okay? I will say, okay, I will form a mathematical problem. The problem is that E is equal to, if this current is I, okay, and if this voltage is V, okay, so I will say E is equal to, let me first write a differential equation, okay. Differential equation is dV V dt is the current, dv dt, C dv dt is the current, multiplied with 0 is how do we first, okay, let me, I'm messing up a bit, let me write the normal equation first. C dv dt, if there is any R, we write into R is the voltage drop plus V is equal to E. That's the normal equation. Now we will put R equal to 0. Okay, acha. So this is the condition. Plus, in addition to that, I give another condition, which is my boundary condition. V0 is equal to 0. That is, the voltage initially is 0. Okay, now what is the solution? What is the solution? V as a function of time. If I ignore this initial condition, then there is a solution, and that solution will be V equal to E. From here, that is the only solution to this differential equation, which is not actually a, I mean, this is a very trivial differential equation. This term is not at all there. So this is the only solution. V of t is equal to E. Now in addition to that, I impose the initial condition, V0 equal to 0. Oh, but there is no such solution which simultaneously satisfies both this. Okay, because here I have only one solution. If there was a R, then when we solve, we get multiple solutions, we get a constant k, etc. And then we can choose the value of k such that V0 equal to 0. But here, this is the only solution to this differential equation. And I cannot satisfy the initial condition, so there is no solution. So I can get away by saying there is no solution to this problem.